Hello everyone, my name is Josh. In this video, we will go through predicting exam scores using studying hours. This is the first data science task under the Graduate Rotational Internship Program of the Sparks Foundation. Here, we will be talking about linear regression, and our goal is to see how the model works in the most practical manner that we can. So let's get started by looking at the background of the problem. We have a small data set of students studying hours and their corresponding exam scores for this examination that they are preparing for. And we want to model the relationship between these two variables. So I want to be clear that we're only modeling the relationship of studying hours and exam scores. This is not going to be a causality test, meaning we are not going to prove that changes in exam score is solely because of studying hours. So, for example, if I studied for longer hours, it is because of longer studying hours. So, it's not going to be our motive or it's not going to be our goal in this discussion. So, we just want to estimate how much. Um, how much change is happening to the exam score for every change in the unit or in the number of hours that was allotted to studying. All right. And using this model, we want to predict exam score of a student if he or she studied for 9.25 hours. So this is an example of a regression problem. Regression is one of the two approaches in supervised machine learning. So let's talk a little bit about supervised machine learning. In supervised learning, we have our input variables, and we are passing these input variables into a function that will process it, transform it, and do some calculations so using the input variable so that we can get an output. So this is the short mathematical equation that summarizes our definition. So our x is our input variable, our f right here is our function or the algorithm. So the f of x, or solving for f of x, will give us y as which is our output. So you just have to remember that in supervised learning, most of the time we are interested in predicting an outcome or an output. And this output can either be a real number or a category or a qualitative data. So based on your output variable, you can classify a problem as a regression problem or a classification problem. So it's if if your output variable is a, a real number, then that's a regression problem. So for example, if you want to predict the sales or the price in dollars or weight in pounds or kilograms, and it's going to be a classification problem if your output variable is a category, for example, red or blue, disease or no disease. And it can also have multiple outcome or categories like different species of a flower or different stages in cancer, for example. We will not focus on classification problem in this video, but instead we'll just have to focus on regression. And our main topic for today's video is that the famous regression model that most data scientists and statisticians use. And I'm talking about linear regression. I like how Yale University defined linear regression. Based on their article, linear regression models the relationship between two variables by fitting a linear equation to the observed data. And to make it more intuitive, I have here the graph or the scatter plot of student studying hours and their exam scores. And this is actually the same data that we will be using later on. And if it's your first time seeing a scatter plot, you read it as here we have the hours. So you just have to go up for you to and stop on that particular dot, and turn left for you to see the score. So for 6 hours, this student got 60 points. And if you're seeing a trend like this on your scatter plot, this means that your variables have a positive correlation, meaning if your x variable increases, your y variable also increases, which is really evident right here. Okay. And another thing that we should look at in this chart is this straight line right here. And this is our regression line. All right. So we want this regression line to be as close to all data points as possible. In this case, this is the best fitting line, I would say, since as we can see, most of the data points on our data set is close to our regression line. If I draw a straight horizontal line like this, I hope that you're visualizing it. It's not going to be a good regression line because most of the data points are far from the line itself. So again, we want this line to be as close to all data points as possible. And you don't have to worry because it's not going to be a manual work of drawing that straight line. So we are using this equation to estimate this straight line. And so just this equation is y is equal to beta naught plus beta 1 times x plus epsilon, which is our error term. Our x is our input and y is our output. What we are trying to solve for us to estimate this best fitting line are our coefficients or our beta values. And of course, for the sake of practicality in this discussion, we are not going to go through the math behind solving for beta naught and beta 1. And of course, since we have R as our tool to solve this regression problem, we don't really need um, the manual computation of getting the beta values. Instead, we will just be using some R functions to estimate our coefficients. All right. So assume that we already know our coefficients. So you just have to plug the values of these coefficients. So we have to plug the value of beta naught, plug in the value of beta 1, and give an example value of x or number of hours. And epsilon or our error term is by default not really counted in our computation, but from the backend it's going to be part of it. So for example, for 6 hours, I have here 6, so I have to multiply it by um, beta 1, and I will add the value for beta naught, and that's going to be my estimated or predicted score if I studied for 6 hours. So this is now using the linear regression model. So where is that in our chart? So you have your 6 hours here, just go straight up and stop on that regression line and turn left. And as we can see, it's roughly at 60 points, which is somehow close to our actual sample here. And that's what we want to happen. We want our predictions to be as close to the actual data points as possible, because that will measure the accuracy of our model. Okay, so that's how at least the simple linear regression works. So this is just a simple linear regression because we have only two variables. Our first variable is our input variable, and our second variable is our output variable. And this equation right here shows us the equation for a linear regression model with multiple variables or multiple independent variables or input variables. So you just have to extend it with extra variables. We have the same formula right here. And I'm just adding beta 2 plus times x sub 2 plus beta 3 times x sub 3 plus until we get the last number of independent variables that we have from our data set. And you don't have to worry, we are not going to use this since the data that we will be using only has two variables. So we can just simply use our simple linear regression model. All right, so that's it for the theories and concepts. So let's now go to R and do some coding. Okay, so right now I am in R Studio and we will go through each code and see how we work on this on an analysis that involves linear regression. Okay, so first we will start by setting a directory so that we can just simply work with our files in just one directory. And I would say that this is the best practice when coding in R. So let me run this, and I'm also importing some needed libraries. So I have here the ggplot2 package for me to visualize the linear regression results later on, and I'm using ggpopr to combine two ggplot objects into just one plot. All right, so let me run this. Okay, next. So right now I'm trying to read the data from the directory that we just set here. So we have the file names students underscore scores hyphen student underscore scores dot csv. And I'm using read.csv function to read the data set from the directory, and I'm assigning it to the students underscore data variable. So let's run this. Okay. And one thing that's good here in our studio is that we have this environment section for you to see all of the variables that you have used during this session in R. And as we can see, we have the newly defined students underscore data, which is our data set. And I can actually click on this for me to see the table that we are working with. All right, and I find it really helpful because I want to see, most of the times I want to see the data in a glance and not just by using some functions in R. So for me to just really visualize what can be the errors of the data and so on. So yep, so this is really a handy tool in R Studio. All right, but if you're not in R Studio, you can still do that similar way or similar feature, and that is by using the head function. So this head function will give you the first few rows of your data set. So if I'm going to run this, uh, I'll just resize the window, and we are seeing the first 6 rows of the data set. So by default, we are um, only seeing the 6 rows if we are using the head function. But if you want to see, a different number of row, then you can just simply add a second parameter. Let's say I want to be the first 10 rows instead. Just add 10 here as your second parameter, and we can now see that we have 10 um, rows in the that's printed out by the head function. Let me go back to default, and we also have the dim function. So this dim function will give us the dimensions of the data, and this dimension is really the number of columns and the number of rows that you have on the data set. And if I run this, we can get 25, which stands for the number of rows, and 2 for the number of columns. But if you have this environment section, you might not need that anymore, since you can see here that we have 25 observations and we have 2 variables. All right. So that's just some of the things that we can try to do firsthand when or before doing the analysis or the modeling itself. We're not, of course, going to go through the entire or the full exploratory data analysis, because our data here right here looks clean already. As we can see, there's no missing values or um, any possible errors on the data. So right now we can proceed by starting with our model itself. All right. So we have here the LM function. So this LM function stands for linear models, and this is what we use to train linear regression models in R. And typically it takes two parameters. The first one is the formula that we are using. So I'm using here the scores column, which is here, the second column of our data set. And I'm using tilde, and I'm using hours, which is the first variable or column in our data set. So this is read as scores equals hours. All right. And if you can recall the model that we have earlier, or the linear regression equation that that I've shown you earlier, um, y, or the response variable or the output variable, is on the left side, while the output variable is, or sorry, the input variable is on the right side. So that's just how you will visualize this. All right, so that's our first equation or parameter. And our second parameter is our source of data, which is, in this case, students underscore data. So I'm training this model using this line right here, and I'm assigning the output to lean underscore reg variable. All right, so let's run this. As we can see, it has been added to our environment section, and it's a list of 12 items, but we're not going to go through this since there are some complexities that you will see right there. All right, but if we print out len reg variable, right, what we are going to see is the coefficients, or the beta naught, or the beta 1 value. So we have, so let me run this. All right, so we have call, which gives us a reminder about the formula that we have used, which in this case, this one, and our coefficients, or the beta values. So we have the intercept and the hours value. Intercept, this is the value that we have for the beta naught, or the beta 0 of our equation. And this is our beta 1 value, right? So it's helpful, or printing out the linear regression object is helpful if you want to see the variables or the coefficients of your model. But we are using a different function for us to extract all of the scores or the results that you really want to see from a linear regression model. So we are using the summary function, and as a parameter, we are passing the linear regression model inside this function so that we can get more output. So let's run this and resize this. And as we can see, there's a whole lot more of results um, in our results, or in our console. So we will go through the most important parts of this output so that we can understand which portion to look at in a linear regression model, and see if the model works for your purpose, or if you need to use a different model or whatnot. Okay, so right now I'm back here in the slides to continue our discussion on regression output. To have a short recap, we used lm function to train our linear regression model, and we have assigned the output on our variable, which we call linreg model. We have used this variable as a parameter of summary function so that we can get this detailed regression output. We will not discuss all of these results. Instead, we will just be discussing the most important ones. All right, so let's get started by looking at our residuals. So residuals are the distances between the actual response variable and the predicted response variable, or predicted output. So here you've already seen this graph before, and we have the regression line, which is the blue straight line right here, and we have all of the observed data points represented by red dots. So the residual here is the red line between the regression line and the observation, right? So that's how far the predicted value is from the actual observation that we have on our data. And accounting for all of the residuals in our regression model, we can get the summary statistics such as the minimum and the maximum, first and third quantile, and the median. And those are the summary statistic that we can get from the regression output. And there's one thing that I want to mention, but we will not elaborate further. So that is our residual plot should not have any pattern or not have any trend when we graph it on a scatter plot. So this is the residual plot that we have on a regression model, and we simply plotted the predicted value and its corresponding residual. But as we can see, there's some sort of curvy pattern that we can observe from our residual plot. So this is something that we can investigate further and see if it's going to make an impact when we use a different data set. But we are not going to do that here since our data set is it's just small, and we are not really going to use a model on other data sets. So that's for the residuals. So let's now continue to our coefficients. Our coefficients are the betas that we have on our regression model. So we have to estimate these beta values for us to complete the regression equation that we have. And of course, we are not going to do some computation or derivation to get these beta estimates, but instead, LM is kind enough for us to give the estimated value of these beta coefficients. So this is the coefficients table that we got from the regression output. So we have the estimate, which are the values that we can replace these betas with. We have the standard error, which is the standard deviation of our coefficients. And we have our t-value, which we can get by dividing our estimate by the standard error, and our p-value, which tells us if our estimates is or are statistically significant. Most of the time, we will only be interested in the estimated coefficient value and the p-value. So we'll just have to focus on these two. We have our intercept. So this is our beta naught value. So our estimate of our beta naught value is 2.48. Intercept is interpreted as the value of your output variable if your input variable is 0. So if we put that in our context, if a student didn't study for an examination, he can still get 2.48 points from that examination. So now we have ours, which is our beta 1 value or beta 1 coefficient. And our estimate for that coefficient is 9.77. And this one is interpreted differently. So here, this is the increase in your output variable for every unit increase in your input variable. So in our context, for every extra hour that you have allotted to studying, you can get 9.77 extra points on your exam score. All right, so that's how we can interpret our beta values. And now we have our p-values. So just to talk a little bit about our p-values, we have a hypothesis test that's going on when dealing with the p-value. And the null hypothesis is that our estimates are equal to 0, meaning our estimates or our coefficients doesn't really have an effect to our model. The alternative hypothesis is that our estimates are not equal to 0, and that's something that we want because we want to see the relationship between our input variable with our output variable. All right, so our goal here, or our what we want to look at, or what we want to see on our p-value is to have a p-value that is less than 0.05. So here, this is in standard scientific notation, but we can simply derive it in a bit. So we have 3.367785 times e raised to -1. So for us to interpret this, we simply need to move the decimal point one place to the left. So that's going to be 0.33. So 0.33 is greater than 0.05. So that means that, our estimate for our beta naught is not significant, or can be equal to 0. But since we are talking about our intercept or our beta naught value, most of the time we are not really concerned about the intercept having a high p-value, because beta naught or our intercept is really part of our model. It's a constant in our model that we can't just take away. So here in this case, it's just fine if our beta value, if our p-value for our intercept is greater than 0.05. What we should be concerned about is the p-value of our estimated beta 1 value. Here we have 9.13262 raised to -17. So here we simply have to move the decimal point 17 places to the left, which is way lower than 0.05. And that means that our estimated beta 1 coefficient is statistically significant, or it's statistically correct. All right. So that's how we interpret our coefficients. So last but not the least, we have the multiple and the adjusted R squared. So our R squared is the goodness of fit measure in our linear regression model. So this is the percentage of the variability of the response variable that was explained by the model. And multiple R squared ranges from 0 to 1, since it's a percentage, right? What we want our R squared to be is to have a value that's as close to 1 as possible if we are wanting the model to predict with high accuracy. All right. So in our case, we have a multiple R squared that is greater than or that is equal to 0.9529. And this is a fairly high R squared. This means that our model can predict with high accuracy, and we can trust the model in our prediction task later on. But what about adjusted R squared? So adjusted R squared will be useful in a multiple linear regression model. That is, if we have multiple variables that we are adding in our model to see if that will make a difference. So for example, here, after we have modeled the studying hours and exam scores of the students, we want to add another variable to our model. For example, I want to see I want to add students' allowance as the second variable in our linear regression model. So if I'm going to do that, I'll need to look at my adjusted R squared to see if it's going to go up or if it's going to go down. If our adjusted R squared went up after adding that new variable, that means that that variable is useful and is relevant to our model. If in case that our adjusted R squared became lower after adding that variable, that means that the new variable is not useful in our model. So we have to remove that from our model so that um, we can take out all of the um, variables that are not useful in our model. All right, so that's how we would use adjusted R squared. Because if you're just going to look at multiple R squared, every time that you're adding new variables to it, it's just going to increase no matter if that variable is useful or not. So that's why we have to look at adjusted R squared if we are adding extra variables to our model. So last thing that I want to mention about R squared is that having a low R squared doesn't necessarily mean that your model is useless. it all depends on your purpose of using the model. So if your purpose is to just quantify the relationship between your output and your input variable, then all you need to do is to look at your um, coefficients. You need to look at your estimated values for your coefficients, and especially the p-values, because that's going to tell you if your estimated coefficient is statistically significant. And if your p-values are lower than 0.05, then that's good because you're able to meet your goal. That is to quantify the relationship between your input and your output variable. But if your purpose is to have a predictive model that can predict with high accuracy, then you need your R squared to have you need your R squared to be higher and closer to one. All right. If not, you might want to add extra variables to see if that's going to work or use a different model. And speaking of prediction, so let's now go to our last objective in this session, and that is to predict the exam score of a student if that student studied for 9.25 hours. I am defining a new data frame called new underscore data, and I am assigning 9.25 to it so that we can denote the 9.25 hours of studying. And I'm using the predict function for us to predict for new exam score. Predict function takes two arguments. The first argument is our linear regression model, and the second argument is the new data set that we will be using. All right, so which in this case, this is the data set that we have, data frame that we have just created here in this line. So running this line of code, we can get 92.90 points. And that means that this is the score that the student will get if a student studied for 9.25 hours. So we want to be good statisticians. And for us to do that, our predictions should have a confidence interval assigned to it, meaning we should be predicting with lower and upper boundaries because we cannot really make sure that our prediction will just fall on that particular level. And for us to predict with 95% confidence interval, we simply use the same predict function and pass on the linear regression model that we have trained and the new data frame that we have created in this line. And the third parameter should be interval, which is equal to confidence to denote 95% confidence interval. Running this code, we can get the same estimate, which is 92.90 points, but we have two extra results from this function. So we have the LWR and UPR, which stand for the lower and the upper boundaries of our prediction. What does it mean is that we are 95% sure that that the student will get 88.31 points, that the student will get between 88.31 points and 97.50 points if he studied for 9.25 hours. So that's how we will interpret the result of a predict function if we have added a confidence interval to it. And let's try to visualize the regression model with confidence interval. So this is the same scatter plot that we have earlier with the regression line, but this time we have shaded region above and below the regression line to represent the confidence interval that we have on this regression model. Again, whenever we are predicting, we are not predicting for just one sole value. We are adding confidence interval so that we can have a boundary of our prediction. All right. So that's just all for this session. So let's just summarize what we have talked about in this video. So first, using linear regression, we have modeled the relationship of studying hours, and exam scores. And the model is estimated by y is equal to 2.48, which is our beta naught, plus 9.78, which is our beta 1, times x. And the r squared that we got is 95%, 95.29%, and the adjusted r squared is 0.9509, which means that the model that we have trained can predict with high accuracy. And something that we can look further is the residual plot of our model. So we can try to investigate and do some further prediction to see if it's going to do the same on other data sets, which some we have not really done that here because we don't have a different data set, but that's something that we need to watch out for every time that we're using linear regression in our real life analyses. And last, we have our prediction task, which is to predict the exam score of a student if that student studied for 9.25 hours. And based on our model, we got 88.31 points and 97.51 points, which are the boundaries of our prediction. And this follows a 95% confidence interval. So that's just it for today. So thank you so much for watching this video, and I hope that you have a good day.